Hello, everyone. Welcome to Talk Nerdy. Today is Monday, November 19th, 2018. Happy American Thanksgiving to my American listeners, and happy belated Canadian Thanksgiving to my Canadian listeners. I hope you guys have a really wonderful week. I'm super excited about today's show. Before I dive into all that good content, I want to thank those of you who made Talk Nerdy possible this week. The kind of biggest supporters on Patreon right now include Rob Schreck, Pedro M. Rosario Barbosa, Phil Tiber, The Zombie Drummer, David J. E. Smith, Jeffrey Perez, Charles Payette, Jafe, Gabriel Felipe Jaramillo Gonzalez, Brian Holden, and Jeffrey Sewell. Thank you guys so very much. I hope that you too are having a happy holiday this week. And I wanted to let you know that there's a bunch of ways that you can support the show. You can go to patreon.com/talknerdy, or you can just visit my website, carasantamaria.com. You can rate and review the show on iTunes, on Google Podcasts, on Stitcher. That's like a really big one. I have like a fair amount of reviews, which is great, but apparently it really does something with the iTunes algorithm. And I think we could stand to boost that number a little bit. Lastly, I do have some new stuff in the Talk Nerdy store. I am starting to offer for the holidays copies of all the books I've been involved in. So I wrote the foreword for the kids' book, Charlie and the Tortoise by MJ Mouton. It's so really fun and beautiful. I wrote the foreword and am the quiz master for the new National Geographic Almanac 2019, which is a beautiful coffee table book just full of lovely photographs and infographics, and also super affordable. It's only $20. And of course, I was co-author on the new Skeptic's Guide to the Universe book. So if you want to grab a copy of that book from the bookstore, that's super great. And I really encourage it. And we're really grateful for all that support. But if you want to buy a copy directly from me at talknerdymerch.com, I'll give you a personal inscription in those books before I send them out to you. So that's always a good idea for the holidays. Also, we just have a lot of really cool merch because I've had some amazing designers contribute to the cause. So I've got t-shirts and hoodies and tank tops and socks and like hats. Some of it's embroidered, some of it's screen printed, just lots of cool options with a bunch of different logos and designs. I even got a new logo that looks just like Killer. It's so cute. I'm going to put up the tote bag. Hopefully that'll be up by the time you guys listen to this episode. I'm not sure if I'll be able to get it on all of the different items. If you're extra interested in it, though, email me and I can see what I can do. But it's super cute, so check it out. That's talknerdymerch.com. Okay, enough business. Let's dive into the fun. This week, we have the amazing opportunity to listen to learn from Dr. Chris Impey. And Dr. Chris Impey is a professor and deputy head of the Department of Astronomy at the University of Arizona. He is an observational astronomer, meaning that he is looking at cosmology through telescopes and other instruments and studies the large-scale structure and evolution of the universe. He has written several really compelling books, everything from The Living Cosmos to How It Ends to talking about life. Frontiers of Astrobiology. Astrobiology is such a fascinating topic. But this week, we are talking about his newest book, which is called Einstein's Monsters, The Life and Times of Black Holes. So, black hole cosmology, gravitational waves, physics, a lot of really cool stuff is in store for you. So I guess it's time to say what I always say. Without any further ado, here he is, Dr. Chris Impey. Well, Chris, thank you so much for joining me today.
Yeah, it's great to be with you.
So I'm really excited to talk about your new book, Einstein's Monsters, The Life and Times of Black Holes. Black holes have always been a conversation on the show, which are A, an enigma to me, but B, are so fascinating to the Talk Nerdy listeners. So anytime I get to dive back into it, it's great fun because it is not my area of expertise by any stretch. I'm glad it's yours.
Yeah, I had to work up to it, actually. I mean, I've written 7 or 8 books, and I had to get up the nerve to approach black holes.
Really? So is there something, especially kind of complex or especially difficult to communicate about black holes that you didn't see in your previous work?
Yes. I mean, I think the enigma of black holes, or the sort of dichotomy, is they attach to the public consciousness. Everyone has heard of them, as many people are afraid of them, perhaps unnecessarily so. and sort of they think they know some stuff about black holes, and the professionals, it's just a very rich research area, and some of the most fundamental questions are still unanswered. It's extremely active. There's all sorts of puzzles and paradoxes and problems that aren't going away. It's just a very rich research field. So it's hard for the public or general audience to make sense of black holes beyond just the idea that they're ruptures in space-time. And it's hard for the professionals to make sense of them for more profound physics reasons.
Oh, gosh, I hope that we have the opportunity to really dive into some of those things with some nuance today. I would say that the first thing that was the takeaway that I learned when I first started talking to people, interviewing them about this topic, was that black holes don't actually suck. That's something that always stuck with me. Is that a really naive way to describe them?
And they have gravity, but it's, from any kind of distance, it's unexceptional. So, the classic example is if the sun, some evil genius alien civilization crushed the sun down to 3 kilometers, which formally would make it a black hole, the Earth would continue in its merry orbit unaltered. We'd all die because, of course, there'd be no sunlight and the food chain would die. But the gravity at a distance, at our distance from the sun or a black hole, is about the same. So all the exotic black hole stuff, the warping of space and time, it happens actually very close to the black hole.
And that's the kind of perimeter or boundary that we call the event horizon?
Yeah, and I would say that the event horizon is, and that's another misconception, perhaps, that people think of it as a physical barrier or boundary. Mm-hmm. I mean, it's really just an information barrier. It's a mathematical derived distance. Nothing really changes. If you were to fall into a black hole, you wouldn't hit a wall or go bump or anything. So the relativity effects, the strong relativity effects, happen sort of a factor of 10 to 100 from the event horizon. So for a solar black hole, it would be, 100 kilometers or so. And by the time you're millions of kilometers away, it's just an object with a certain mass pulling you in with a certain strength.
Just like any other large object within the cosmos.
So that, hits one of the big misconceptions that they're cosmic vacuum cleaners hoovering up everything around, in some maniacal way. And they're not really doing that. I mean, first of all, space is incredibly empty. Second, black holes are incredibly rare. Only a tiny fraction of all stars die as black holes. And third, their gravity, far from them is just the same as the gravity of any object. And so, it's a little disappointing, actually. Maybe I shouldn't be hitting such a downer note so early on.
Is it true, though, that black holes are at the core of many galaxies, kind of like our own, like supermassive black holes?
Yes. And I think that's when I was writing my book, that was sort of what I wanted to balance out, that, most people are familiar with black holes that result from the death of a massive star. And those are the first black holes that we showed to exist in the late 60s, early 70s. But a little more surprising was this sort of realization, actually over 10 or 15 years, it wasn't a single aha discovery in astronomy, that essentially every galaxy in the universe, so that's 100 billion of them, have black holes at their centers, and those black holes sort of scale in mass with the galaxy that contains them. And we didn't know this for a long time because only a few % of them are active or, chewing up gas and stars and spitting out a lot of energy. So when they're dark objects at the center of a huge stellar system, it actually is quite hard to show that they sit there in the middle of a galaxy. So it took a while for people to realize that.
And how did we figure that out?
Well, a lot of it happened. So there's the special case, of course, is our own galaxy, where the black hole and the center of the galaxy are only 26,000 light years away. So we have a bird's eye view, a sort of, ringside seat for that black hole. But it turns out to be a rather modest one. It's only 4 million times the mass of the sun. The biggest black holes in huge galaxies beyond ours are 1,000 times bigger. So our galaxy's black hole is very nearby, but it's also quite small. And it took a while to figure it out. Also, when we look to the center of our galaxy, we're in the disk, in the plane of the galaxy, and there's just a ton of dust and gas. So visually, you can't see the center of our galaxy. It basically, from the region around the black hole in the center of our galaxy, but only about 1 in a trillion optical photons reaches us. So you have to use infrared or radio methods to see the black hole in our galaxy, and so that's part of why it took a while to figure it out. For the more distant galaxies, or the black holes in all the galaxies we have around us, pretty much the Hubble Space Telescope broke that open because it had this sharp vision, once its optics were fixed, to drill down into the center of the galaxy and sort of isolate a nuclear region and use spectroscopy to see stellar velocities and gas disks moving really fast and sort of infer that there was a dark object there. And that really pretty much took a decade to do that kind of research. So it was a slow and steady realization that, every galaxy really does have a black hole, and most of them are dark and not active. So that was why we didn't realize it for a long time.
Oh, that's very cool. So to break down just a few terms in there, in case if anybody is getting a little lost, when we talk about ways that we can measure what's going on around us in the cosmos, we have a lot of different tools, and we usually think of looking into space with our eyes. We say looking, we talk about light, and that's part of the electromagnetic spectrum. You mentioned IR, you mentioned radio, like there are different ways that we can look. You also mentioned spectroscopy. So there we're not, like, what are we doing with the light when we are doing spectroscopy?
Right. So it's really a critical tool of astronomy. I mean, modern astronomy would be, a shadow of itself without spectroscopy as a tool. So basically, we're just taking the light we might gather with a telescope, and dispersing it into the wavelengths. I mean, you could do it with a prism, the way Newton did with the light from the sun coming into his office in Cambridge hundreds of years ago, or you can do it with a spectrograph at a big telescope. And it's a pretty standard toolkit of astronomy. I think about half the observations on most major telescopes now, including the Hubble, use spectroscopy. They don't actually take a picture or a direct image because spectroscopy is so powerful. And of course, what it does is, apart from dispersing the light into a spectrum and seeing whether an object is red or blue or how much of the different colors it has, it lets you see the spectral features which tell you what the gas or stars are made of. So it allows you to see the elements and their relative abundances. So that's how we figured out what stars were made of 100 years ago. It's how we figured out that the Andromeda galaxy was not a part of the Milky Way, and that Hubble showed that galaxies were distant and moving away from us. That was spectroscopy. And it's how, more recently, we showed that there are black holes in the center of galaxies. So many of the biggest discoveries in astronomy for a century have used spectroscopy.
That's very cool, because certain elements, for example, hydrogen or helium, have a different signature that you can actually pick up with these tools.
Right. So the two things you can do pretty easily are you can disperse the light and recognize the pattern of each element. It's like a fingerprint. The spectrum of hydrogen is completely different than the spectrum of helium or copper or iron. And then when there are all those elements together, they just add together, making the spectrum kind of complicated. But you can disentangle it. So you can say what the chemical composition of a star is, or a galaxy. And then by referencing the position of those lines with something that isn't moving in the lab or in your telescope chamber, you can say, using the Doppler shift, whether the object you're studying is actually moving away from you or towards you by the Doppler shift.
Oh, it's so cool. See, guys, if you're studying physics or chemistry or even biology in school right now, and you're like, why do I have to take so much of this other field of science? Now you know. There's a lot of chemistry in physics. These two things are really important to understand. And also, this does remind me of an earlier episode in which I had the opportunity to interview a very good friend, Holly Bender. So if you guys remember that early episode, Holly is an optical engineer at JPL. So we dig deep into how these different tools work, because she actually makes the lenses for them, and we call her the mistress of space rainbows.
Wow.
So of course,
nice title.
Right? There are, of course, so many incredible discoveries in science, especially like right now we're talking about black hole research, that just simply wouldn't be possible or wouldn't have the resolving power that they have without new innovations in technology. And gravitational waves are a perfect example of that, aren't they?
Yeah. I mean, that's really an amazing physics experiment. It's, that detection is 100 or 1,000 times more sensitive than any physics experiment in any lab. So they sort of broke new ground in just the precision of a scientific experiment, just to be able to detect them at all.
And so I'd love to talk a little bit about, some of the newer findings in gravitational waves. The fact that it's not just, there was this cool experiment done, but that it's basically like we have a new, in essence, a whole new type of telescope, like a whole new way basically to measure stuff that was happening in space.
Right. And I think the way I like to think about it is in that you just take the big picture of astronomy. That in the history of astronomy, since, humans originated, there have only been a couple of innovations. The first was, and so we've been doing naked eye astronomy, obviously, for tens of thousands of years since people looked up and wondered about stars and noticed that they had colors and saw there were moving objects in the sky. And then there's Galileo. So now you can assist your eye and gather more light. And I think his best telescope gathered 100 times more light than a naked eye would. Mm-hmm. That's a modest gain, but the deepest picture with the Hubble Space Telescope is 100 billion times more light than you can gather with your eye. So the march of optical astronomy it's really just doing the same thing still. It's just assisting the eye to see more light, gather more photons. Then the second revolution, it doesn't happen in one time in 1 year. It's the technology of the early 20th century that opens up the electromagnetic spectrum. So for those whole 400 years since Galileo, you've been essentially staring at the universe over a factor of 2 in wavelength of radiation, from the bluest blue to the reddest red. It's only a factor of 2.
Yeah, it's a tiny little band.
Yeah. And with the opening up of radio initially, because that was Marconi, it's literally 100 years ago. And then eventually infrared, X-ray, gamma ray, all the other forms of electromagnetic radiation, all happening sort of in the 50s, 60s. Now you actually have a factor of 1 trillion in wavelength. And that's incredible. I mean, the longest waves are meters long. The shortest waves are smaller than the nucleus of an atom. And it's as if, the analogy that people use is like a piano. So you've spent 4 centuries just playing with 2 white notes adjacent to each other. Well, you can make a little music, but not very interesting. And then suddenly you have the whole piano, all the octaves. So that was the second revolution. And we're still benefiting from it because the technologies to detect, especially gamma rays and X-rays, they're still improving, and infrared. And that's it. There's been those 2 revolutions, and gravity waves is the third. I mean, it's the only dramatically different way of talking to the universe. And it's as if you had gravity eyes now. So everything we've done with radiation, whether it's visible light or X-rays or gamma rays or radio waves, they're all still the same thing. They're just electromagnetic radiation. Mm-hmm. And that's radiation that comes from matter. It's emitted by matter, it bounces off matter, it's absorbed by matter, but you don't actually see the stuff directly. So it's a messenger of the stuff of the universe. When you look at gravity waves, you're seeing the stuff directly. Like I said, as if you had gravity eyes, because you're looking at mass and how it changes and how masses interact with each other, with nothing in between, with no mediating force or radiation required. So that's a dramatically different way of looking at the universe.
So many amazing analogies that you used in there that I think really do help somebody who maybe doesn't have the grasp of the mathematical language of cosmology or even some of the fundamental training in physics to really wrap our heads around these phenomena, which are a little bit difficult and often, I think, taught to us in a way that doesn't always do them service. So I would love to kind of break down really quickly the sort of, the chain of what's happening when we detect a gravitational wave. And maybe you can sort of help me improve or iterate my thinking on this, because the best that I understand is that you've got these 2 black holes out there in space somewhere. Mm-hmm. They collide. And when they collide, it actually kind of ripples the space-time around them. It makes a wave similar to maybe what we would think of as a sound wave or a ripple on the water. And that ripple, passes through space. Mm-hmm. And eventually, we on Earth are going to be in the path of that ripple. And we set up this crazy cool experiment where there's these really long arms that are a very particular distance apart. And we could predict how long it would take for a little perturbation to happen at one arm versus the other arm. And when those things matched up, we knew that we were actually detecting that gravitational wave. Is that like kind of what happened?
Oh yeah. That you nailed it. That's pretty good.
Oh, good.
And
Jan 11 helped me with that. I have to say.
She's great. Then the thing I would say at the beginning of the whole chain of the whole process is that the prediction of gravity waves came out of general relativity, and just as with black holes, even Einstein, the architect of the theory, didn't think they really existed. I mean, he thought either that they were an artifact or an anomaly. He didn't like the singularity in particular because that's an infinity of mass density, and that's awkward. Physicists don't like that. So Einstein kind of just sidled away from a prediction of his theory, and gravity waves is another prediction, and he pretty much didn't follow that up either. And gravitational lensing is another prediction that he didn't really do anything with or pursue. So,
oh my gosh. So they worked in the modeling and the math, but he thought, we'll work that out later because it can't possibly be an actual phenomenon.
Either that, or sometimes it appeared. He probably also thought it was undetectable. There was not anything astronomers could ever measure, and that's happened a lot in astronomy. In the relationship with black holes, the next less dense objects in the universe are neutron stars, and they were also predicted in the 1930s using general relativity. And that's a pure atomic nucleus with an atomic number of 10 to the power 57, emitting no light, made of pure neutrons, and the theorists were excited. It was really cool. And the observer said, okay, how are we supposed to detect that? A huge atomic nucleus that doesn't emit light, that's so tiny, it's the size of a small city and probably it's trillions of miles away. Get out of here. We're not going to find that. And indeed, it was found by accident with pulsars 35 years later. So a lot of the predictions out of general relativity were just sort of set aside because they either were thought to be artifacts and not real physical things, or they were thought to be impossible to detect. And gravity waves are definitely in that category, because when you do the simple math, it's not simple, of course, that's being facetious with general relativity. You deduce that, it's a very general phenomena. Basically, gravitational waves result from any change in mass or a mass configuration. So it could be a single star that loses mass. It could be a star that's spinning and it's not symmetric. Maybe it's not completely spherical, or more dramatically, it could be colliding black holes or neutron stars. It could be a supernova that goes off and it's not completely symmetric. So any change in a mass configuration will emit gravitational waves. The trouble is their size, their amplitude is, and as you said, they are indeed space-time undulations or ripples. They could be, there are different kinds. They can be rarefactions and compressions, like sound waves are with air molecules, or they could be transverse waves like light is. All the different modes of vibration are possible with gravity waves. But when you go through the math, the amplitude, the size of the deviation of the space-time is ridiculously small. And in fact, in the LIGO detector, they're detecting a space-time ripple that's 1,000 times smaller than the nucleus of an atom. And again, if you just proposed to do that before they actually did it, people would just laugh. So, and then of course, it's a ripple in something that's invisible. I mean, we don't see space-time. Space-time is a vacuum. It's empty. And so the idea of seeing a distortion or a ripple that's that small in something that's not visible in the first place, it just sounds outrageous. And so, LIGO is truly the most spectacular scientific experiment ever, I think, just because the audacity of trying to do it and then succeeding, it's just incredible. And then I would, of course, add the audacity of being able to get close to $1 billion out of, hard-nosed funding agencies and skeptical Congress people. That's pretty amazing too. So they succeeded in many ways.
It's one of those interesting things where I'm in my mind kind of juxtaposing the statement that you made about Einstein, really maybe requiring these things as part of the theory, but not having a lot of confidence or even honestly a guess that they either really do exist and aren't artifacts, or if they do exist, saying this is probably something we'd never be able to measure anyway. And then, like you said, the audacity of the architects of the LIGO experiment, which is, of course, the two big arms we were talking about, saying, you know what? I know it's a long shot, but yes, it's worth, as you said, all of this massive financial investment, because I really think deep down we're going to get a detection. Like I don't know. I don't know if I would have put money on it. Would you?
Right. I think I don't know if I would either. And the story of that project is fascinating because, of course, it did not happen overnight. It took decades, and there were false starts. There was a particularly bitter false start because Joe Weber, a very well-known physicist at the University of Maryland, claimed to have detected gravitational waves in the mid-1960s. And then it turns out that it was impossible with his instrument that he could have detected them. And so he was looking at artifacts or noise. And unfortunately, he sort of doubled down and continued to claim the detection. And his career went in the toilet because of that. It's a kind of a bitter story in physics and astronomy. However, ironically, although his failure in the 60s could have trashed the whole field forever, it actually inspired these experimenters, these are basically experimental physicists doing this work, to just say, well, we can do it. They were challenged by his failure and by their belief, not shared with Einstein earlier on, that these really were detectable and real effects of relativity. And they wanted to be able to test relativity in a brand new way. So gravitational waves do let us test our best theory of gravity in completely new ways. That was one of the lures. They let us see the universe in a completely new way. That was another lure. And for people who like to build gizmos and instruments, it was an incredible challenge, and they rose to the challenge.
Was that the BICEP 2 findings that were attempting also to look at something similar, but through the cosmic microwave background radiation? Was that an extension of those experiments you talked about in the 60s, or was that a completely other attempt that also, I don't want to say failed, but gave us some sort of false good news for a while?
Yeah, that's a tricky field that they're working in. So what they're doing is using the microwave background radiation, the relic radiation of the Big Bang, and they were trying to use extremely subtle signatures in that radiation to diagnose gravitational waves in the early universe, but indirectly. So they were using a radiation method, using these microwaves to get at gravity waves in the early universe. And they were testing the inflation idea as it happened. And their problem was it's an astrophysical or an astronomical experiment. And those are messy. If the physics experiments are a little cleaner because you have your lab and LIGO is a controlled environment and everything's in a vacuum tube and you can test your lasers in the lab and then put them in a place where you can test them again. As soon as you're observing the universe, things get messy and ugly. And the only mistake they made is that they didn't model the foreground signals that were sitting in front of their signal of the early universe. So the Milky Way has dust in it and it has stars, and you have to subtract out the stars to see the microwaves clearly, and you have to measure the attenuation due to dust and understand it. And they just didn't model those other signals well enough, and it turned out they were contaminating what they thought they were measuring for the early universe. It was a classic mistake in astronomy, and they were probably a little quick, to the punch of publishing. They might have been a little more cautious, but that's the catch-22. These are very competitive fields. Nobel Prizes are on the line in principle. So it's very hard for these groups to withhold their first result if they believe it.
Oh, absolutely. And it's a classic mistake in basically almost every field of experimental science, in the sense that, contaminants in the data often mislead researchers. And, it's like the number one classical thing that you learn when you're taking, let's say, a multivariate, statistics course, is that like garbage in, garbage out, because the analysis is going to work regardless. And you have to know whether or not the data are clean and that they're valid, that you're actually collecting data that you're looking for and not, artifacts or noise or something like that.
Right. And for people like you and me, people who communicate science to the public, these are important lessons, because people can fall into being too credible, too credulous about scientists. These people with PhDs, they know what they're doing. They said this must be true. And the fact that, or falling to the other extreme, well, these people don't agree with each other, or arguing about theory X versus Y, or
so how can I trust them?
So I won't trust any of them. And so I think, for people who have the patience to look at the whole story, it's a beautiful lesson in how science works and how it is self-correcting. So when Weber published his gravity wave detections in the 1960s, there were theorists who just said he couldn't possibly have detected those signals because what he claimed to have detected was 1,000 times bigger than what the math says it should be. So the theorists didn't believe him for that reason. But it was really just the experimenters showing that he didn't detect that, but detected something else that kind of, reset the field and said, okay, we can still do this experiment, but we have to do 1,000 times better than Weber did. And it took them 20 years to get there, but they did.
Absolutely. And I love talking about these kinds of scientific stories in that context, in a very narrative style, when we talk about the history of science, because I personally believe, as I know that you do through the writing of your book, that what we know now doesn't mean much if we don't look at it contextually and if we don't understand how it is that we got here. And so I think your book does a beautiful job of talking about the history of what we know about black holes, all the way up through some of these modern technological changes in how we're detecting them, measuring them, learning about them. And of course, to sort of the future and the fate of maybe what new modeling is going to share with us. I have to ask you about the cover, at least what I'm assuming is the American version of the book, which I have in front of me, which has like this beautiful, it looks like a Hubble deep field background. Mm-hmm. And then it's like a white room with an eyeball and a square cut out of the ceiling. And what is the symbolism of that?
I worked with the designer on that, or my publisher. They enjoy astronomy books because they can get a little out of the box on their design. Yeah. And I kind of encourage them to do it because it's fun. I don't think it's not meant literally or to tell a story or even metaphorically. I mean, it's just obviously conveying some deep weirdness of the black hole as a concept.
It's very surrealist.
As a window, right, as surreal. And they are surreal objects, as a window on the universe, something we can see but is also inward looking because nothing can escape. So there's no radiation that escapes. And so only the black hole actually really knows. So I think they were just having fun with it, and that's kind of nice. So it's a loose. I kind of like scientists can be terribly literal minded sometimes. So I kind of like when we're working with a graphic designer, you can just be a little loose.
Okay, everyone, I want to take a quick break to thank the sponsors of this week's episode, starting with Crick Start, super yummy snacks made with cricket powder. They taste really good. They're good for you. And of course, I think what's the most important about them is that they're all about sustainability. This is the future of food, you guys. So these are snacks, crackers, and protein bars that are made from cricket powder. So don't worry, there's no like antennas or legs or like weird little crunchy bits. It's all powder. You don't know there's crickets in there, except, cognitively, which is good because you really do feel good eating these protein bars. They're actually really delicious. I think they taste better than those gummy, chalky protein bars that you usually get in the store. And they have yummy flavors. Like there's a cardamom flavored one that I'm really partial to. And they're really good crackers too that you can dip in hummus. You can eat with cheese or with guac. And they're good for you too. They've got like lots of seeds and seed butters and hemp and yummy things like chocolate and dates in them. The great thing is you can keep them in your bag so that you've got food on the go. They're quite balanced, they're really high in protein, like twice as much as beef or chicken. They've got all the 9 essential amino acids that are necessary for muscle growth and repair. And they've got other vitamins and minerals in there, kind of. So they've got the macronutrients and the micronutrients that you need. But here's some fun stuff. Over 40 crickets in every bar, over 100 in every cracker bag. But don't worry, you don't notice them. They're powder. For the same amount of protein compared to beef, crickets require 12 times less feed, 2,000 times less water, thousands of times less land, and they emit 100 times less greenhouse gases. So just for that reason, you should give them a try. All you've got to do is go to crickstart.com and you'll get 20% off of your order, but you need to use the promo code NERDY. Okay? So that's crickstart.com and you'll get 20% off with the promo code NERDY. I also want to thank Adagio for their support of the show. And Adagio is perfect for you if you're a serious classical music fan. And I mean really serious, like somebody who wants to listen to Beethoven Symphony No. 9 by comparing 150 recordings all on one page and filtering them by conductor or orchestra. Because the truth of the matter is, when we try to find good classical music on traditional streaming sites, oftentimes there's only like one version of the specific song that we're looking for. We can only find a single arrangement, or we can only find a single performance. And lots of pieces of music simply aren't there. But with Adagio, they have a massive catalog of incredible work. They've got exclusive content and hard to find pieces. And of course, maybe you don't know the particular work, the particular recording, or the orchestra, or the composer that you want to find. Maybe you just know you want to listen to really good classical music to suit your mood. They have an incredible mood player that helps me find just the right piece. So yes, there's the Composer's Essentials playlist, so you can get your Vivaldi, you can get your Chopin, you can get your Holst, whoever you're into. There's a really cool playlist like Slow Piano. But what I love are like the Come Heavy Sleep playlist, the Relaxation playlist, the Stay Focused playlist when I am trying to write a paper for school. Guys, there's so many options with Adagio. The sky's really the limit. So why don't you try it right now for free? You've got 14 days absolutely free. And then you only have to pay $9.99 a month when you subscribe. All you've got to do is go to podcast.adagio.com/nerdy. Again, that's podcast.adagio, IDAGIO.com/nerdy. All right, guys, let's get back to the show. So I've talked to quite a few people on Talk Nerdy up to this point, because we're in the like 230 something, 40 something numbers of episodes now. And when I talk to people about black holes, for example, I find that there are similarities across the conversations, but I also find that there are very unique perspectives from different people depending on their field of astronomy. So you're currently or a distinguished professor in the Department of Astronomy at the University of Arizona. What type of astronomer are you? Like, obviously you are focused on cosmology, but are there, I've talked to, let's say, string theorists, for example, have very different views on black holes than, people who study sort of Einstein's equations and things like that.
So, first of all, truth in advertising, for a couple of years, I've been an associate dean. So I'm a sort of administrative droid for half of my time. So the pleasurable astronomy part and using telescopes is less than it used to be, but that makes me enjoy it more, actually.
Absolutely. And it means that you get to make bigger decisions about funding and about the people who get to tell these important stories and do this important research. So I want to just update right here in my notes that you're the associate dean. All right.
So I'm an observer, and I cut my teeth. I'm a Brit, and I did my undergrad and grad work in London and then Edinburgh. And so I've been an optical infrared observational astronomer, and I got taken by these very luminous, so we're talking about black holes and their range of masses. So the extreme ones are billion or more solar masses, and they're the centers of large galaxies. And the most extreme of them are the ones that are chowing down on gas and stars and emitting huge amounts of energy. So that's another little paradox built into black holes. People think, well, they're dark, nothing can escape. So how do you see a dark thing? Well, many of them are dark and hard to detect, but a small fraction, a few percent, are very active because they're fueling through an accretion disk. So it sort of matter is falling onto them, going into this equatorial disk and then funneling into the black hole. And they end up being incredibly bright. So when they do that, they become quasars, is one of the terms for these very active black holes. And that's an extraordinary thing. So early in my career, I was drawn to that because what a quasar is it's a nucleus of a galaxy. It's the region around a billion solar mass black hole where energy is being pumped out because of accretion power, and it shines up to 1,000 times brighter than the entire galaxy that contains it. So I would like to use the analogy of, imagine you're hovering over Los Angeles at night in a helicopter or a small plane, and imagine every street light and house light and car light is about 1,000 stars, then you'd have a rough model with a sort of 100 million or a few 100 million lights in the greater Los Angeles region for a galaxy. That's just looking down at a galaxy. And now you have to imagine a source of light in downtown LA that's a centimeter across, that's 1,000 times brighter than the whole city that surrounds it, and that's a quasar. It's pretty amazing.
That's definitely something you want to learn a little more about, investigate a little further.
And the other amazing thing about it, apart from the mass of the black hole behind all this and this incredible amount of energy coming out of a small space, is that it's incredibly efficient. This is, except for antimatter annihilation, which is, of course, 100% efficient way of getting energy, but there's no real world example of being able to use that. These quasars are sort of gravity engines. That's how we like to talk about them in extragalactic astronomy, gravitational engines. And they're, through this accretion power, they're turning gravitational energy or potential energy into radiation with an efficiency that's 40% of E equals mc squared. So that's about 100 times more efficient than stellar fusion, the way the sun shines. So they're incredibly efficient gravity engines, pumping out vast amounts of energy. They're particle accelerators, sending beams of plasma into space at 99.999% of the speed of light. I mean, just wow.
And is that those like ejection kind of jets that we usually envision when we see pictures of black holes? Okay, all right.
And they're interesting because they scale. One of the reasons physics is cool, so physics, as you know, is the gateway drug to astronomy. So, I was a physics nerd before I was an astronomy nerd, and physics, these kind of phenomena, a spinning black hole with matter going into it, they completely scale similarly. So the little picture you have, the little model or the artistic impression is the same whether it's a single star that died or one of these billion solar mass black holes in the center of a galaxy. The physics pretty much is similar.
So, okay, I mentioned before, well, wait, I want to try and follow two trains of thought at the same time, which is never easy. So I scribbled down a note. I have to take us out of this conversation for a second to ask you, first of all, you're British? And second of all, why do you sound like Matthew McConaughey? Have people ever told you that before, that you totally have his same accent?
Well, actually, I'm a Scot, but if I used my original accent, you wouldn't understand some of the things I was saying. So I need a single malt whiskey to for the accent to come back properly. So I go home and that happens here.
Oh my gosh. I was just in Scotland, like literally 2-3 weeks ago, and fell in love with the people, with the land, with the accent, with the Highlands. We were on a book tour, and at the end of our the episode that we recorded there for the Skeptic's Guide to the Universe, I actually sang Loch Lomond live in the pub, and I all these like big burly Scottish men were like, you brought a tear to my eye.
I'm sure you made a lot of fast friends with doing that. So I'm obviously. The accent shows I'm a transplant. My parents moved around a lot when I was little, so I grew up transatlantic, and the accent went away because of that.
And where in America have you lived?
Well, I was a kid in New York from age 5 to 13, and in Boston, and then we went back to Britain where I went to college, and then I came on a postdoc to Caltech, and then one in Hawaii, and I've been in Arizona 30 years. So you've
been in Arizona for 30. Okay, because it's definitely. I'm from Dallas, Texas. You definitely have a twinge of a Texas, very Matthew McConaughey accent.
Okay.
It's so interesting to my ears.
Well, Arizona's full of transplants, of course. So, I'm surrounded by all sorts of strange, mushed up accents from various places.
Oh, I love it. It's unique to say the least. Anyway, so that was my random aside. But the other thing that I wanted to ask was, when I interviewed, for example, Brian Greene, who is, a string theorist. And of course, even within the string theorists, I did an interview of 3. I think it was Michio Kaku, Brian Greene, and James Sylvester Gates all at once. And they all even had different opinions about things. But Brian talked a lot, and it still sticks with me, about this information smearing phenomenon, kind of like this theoretical idea of what actually happens to matter, or maybe we should say information, as it enters into a black hole. And he had some interesting ideas. And I was wondering, A, how mainstream are those ideas within physics? But B, like, are you into that theoretical place? Do you sit and wonder about what's happening on the inside of a black hole, for example?
Yeah, sure. I mean, it would almost be a waste of the energy of being a researcher in black holes, even if you're an observational or experimental person, not to think about the theory, because the theory is so fascinating. As an observer, as an experimentalist, if you like, I'm a skeptic about theories. I mean, in any area where there's uncertainty or ignorance or things are not fully developed, or actually we know there are problems. I mean, it was Hawking who said that black holes sow the seeds of their own destruction in terms of theory, because they're not really understandable in terms of the theory we use to describe them, general relativity. So, that's, for the theorist, that's a rich ground for new speculation and new theorizing. For an observer, the average experimentalist or observer they'll have a slight smile on their face and their arms crossed and say, okay, give me a prediction I can go and test. You guys can have fun comparing your theories, but I want to test something. And that's sort of where things stand with information theory. So there is an information paradox, if you like, and it points to a deep conundrum, a deep tension between microscopic theories of nature, particle physics, and our gravity theory, because the gravity theory and the standard description of black hole does indeed say that information is trapped, that the event horizon is a one-way information membrane where nothing can escape. But particle physics sort of says that particle interactions are fully reversible, and you have to be able to follow quantum properties in particle interactions, and that includes in and out of a black hole, through the event horizon. And out of that tension arise a lot of interesting ideas. That's where the hologram theory, that maybe information is coded on the event horizon somehow. That's where the idea of a firewall comes from, that somehow maybe these particles get entangled somehow, quantum entanglement. But if you break the entanglement, you lead to this firewall outside where information is destroyed again. So,
oh, yeah. I remember, I think John Preskill talks about that quite a bit.
So these ideas are all absolutely valid and in play, and they all essentially emerge from the same tension between two of our best theories of nature that are essentially irreconcilable in the context of a black hole. And that's where the theorists are having their fun. Now, the observers are, saying, okay, tell me how I can test this. Stephen Hawking predicted the thing that made him famous, of course, is Hawking radiation, the fact that black holes have temperature, that they're radiating energy with a very small temperature, and they're evaporating. And not one of those predictions, he was justly famous throughout his life and after his death, but none of those predictions have been tested, and some people think they're not even testable. So black hole theory is an interesting beast because it marches far enough ahead of observations that that the observers are a little frustrated. We're still stuck on trying to show that event horizons actually exist, and that's the experiment that people hope to do with the black hole in the center of our galaxy using this event horizon telescope or radio array. And there's some people at my university and department are doing that. So the observers are doing the best they can with the tools they have available. And of course, that's why that's another reason why the gravity wave detection, and especially when LIGO comes back in February, I think, in a new, with new sensitivity, maybe detecting merging black holes every week or every 2 weeks, it'll be incredible, because it is the sort of maybe not as remarked on as it should have been thing about LIGO and the detection is that was the first time that the existence of black holes was proven beyond any doubt. I mean, nobody could refute black holes. Before that, we had all these black holes in the center of galaxies and all these binary systems with a black hole. They're all subject to models and uncertainties. And, you could wriggle your way out of any of those individual cases. But when you have that classic signature, that chirp pattern, that ringing signal of black holes merging, when you have space-time distortions that only can arise out of general relativity, it's just a slam dunk. So I think that was not actually commented on enough. Like, you can take black holes off the might exist, probably exist pile and put them on absolutely they exist.
Oh, wow. And so, okay, there are three things that I kind of scribbled down while you were discussing that. And the first one is that it's interesting that black holes are sort of in this cool place where they're maybe, perfectly pulled, torn, Venn diagrammed between theoretical and observational physics right now, where there are a lot of things that, obviously there's an important place for observational physics, and there are a lot of things that are still kind of purely theoretical, but that black holes really do sort of require or engage in the know-how of physicists across the spectrum, no pun intended. The other thing I was going to say, which was an aside, is that it must have been so cool to study at this particular thing at Caltech, simply because, and maybe it's because I have hometown bias because I've lived now in LA for so long, but there's so many incredible research. I mean, famously Kip Thorne just got the freaking Nobel Prize for like, there's so many great researchers who are studying this stuff.
That's right. And when I was there, I was postdoc, so that was a while ago. There were all the bets. That part of the physics department has these bets. And there was the famous, as yet, when I was there, unresolved bet between Thorne and Hawking, where Hawking bet against the existence of black holes. And he said he was just sort of, covering himself so he'd win either way.
Yeah.
And that bet was unsettled. There was also an information paradox bet. And there's, I think, about 4 black hole bets that are on the wall of the bridge building at Caltech. And they're unresolved, because the observations are too hard, really.
Oh, that's so cool. And so the other thing that really struck me just then in your discussion was that I guess I was completely unaware that we had no direct confirmation or direct observational evidence of the event horizon, that really is still somewhat theoretical.
And that's right. And it's really because it's so small. So, it's for us, the minimum massive star dying as a black hole, it's a 10-kilometer radius. That's a tiny, tiny object. The nearest black hole, so just take Cygnus X1, that was the archetypal black hole. That was the first time people really thought they had evidence they might exist. That's the late 60s, early 70s. That black hole, that object is 6,000 light years away. So that's another part of the black holes aren't going to eat us all up. They're so rare that the very nearest examples are hundreds of light years away. So there's thousands and thousands of stars closer than the nearest black hole. Cygnus X1 was 6,000 light years away. Well, that's 6 trillion times 6,000. I can't do that math. 36,000 trillion miles away.
Lots of zeros.
And you're trying to look at something that's a handful of miles or a dozen miles across at that distance. Simply impossible. So the issue of resolving, which is to say, seeing the size of an event horizon with a telescope, is absolutely impossible. It's not even close with the black holes in our galaxy. So it turns out that the first and best case where you could resolve it, see the size of it, the shape of it, see the distortions of space and time, the light wrapping around it because of lensing, is the one in the center of our galaxy. Because although it's because it's millions of times the mass of the sun rather than 10 or 20 times the mass of the sun, and it's 26,000 light years away, which is only 4 times or 5 times further away than Cygnus X1. So that's the experiment that people are going to be able to do. That will be the first experiment to image the event horizon. And really what you'll see, since the event horizon is, again, just a construct, it's not a physical barrier, it'll be the way it's backlit, because there'll be luminous glowing gas behind it. And so by seeing the event horizon backlit and watching the way light, bends and distorts and warps around the intense gravity of the event horizon and regions near it, that'll be a brilliant test of relativity.
Oh, wow. And is that also what we see, or similar to that is what we see in gravitational lensing?
Yes, it's just a really strong form of gravitational lensing. I mean, you can just think of, people sort of forget in the math of black holes that at twice the distance of twice the Schwarzschild radius, which is the radius of the event horizon formally, there's an orbit, there's a bound orbit. And in principle, a photon will just go round and round in circles around a stationary black hole at that distance of twice the event horizon. And you could just think of that as just complete lensing. It's just lensed back on itself.
Oh, wow. And so the idea is that if you have a perfectly symmetrical and a relatively stable black hole, that it is going to have just things orbiting it.
Right. And the matter, there's an innermost stable orbit, and that also emerges out of the theory before matter or particles or whatever it is plunge straight into the black hole. And people, really think they've already observed matter. Actually, there's a news story just a week or so ago where they think they've seen a blob of plasma on that innermost stable orbit of the Milky Way's black hole, and they're just watching it. There are these stars like S2, which is one of the few dozen stars that people have been watching looping around the black hole in the Milky Way's center. And S2 gets very close to the event horizon, maybe a factor of 10 away from it. That's pretty close. And its orbit will have strong imprint of relativistic distortions. So those experiments are really on the table now. But that's really the only black hole where you can do that. Unfortunately, the other huge black holes in distant galaxies, they could be bigger than the Milky Way one, but they're also thousands of times further away. Yeah. The stellar mass black holes are so rare that they're pretty far away and they're much smaller. So we're still stuck with looking at, the very best case where we can see these effects.
Oh, yeah. I mean, oftentimes throughout the history of scientific inquiry, it's about kind of, doing your experiments, doing your observations on things that you have within reach, things that you are capable of being able to try and measure and manipulate. Lately, I feel like I've had this shift in the way that I try to visualize gravity. When I was growing up, and of course, my background is in science, but it's exclusively in biology, neuroscience, and social sciences. So there's a lot of statistics there, but there's very little to almost non-existent, I should say, geometry, calculus, basic physics. And so when I was growing up, I had an idea in my head that gravity was a force, and it was a force that, drew things to it. Like that's how it's often taught. And you've got two things that are really massive, that they will have these gravity fields around them and they will be drawn to one another. Whereas more and more often, I'm thinking of gravity as this indention or this kind of, I don't know, maybe indention is the best way to put it, of space-time, basically a rippling, a warping of space-time around something that's massive, so that if something happens to be traveling on a trajectory past it, but space-time warps towards it, it'll fall in like a drain. Right.
And that's right. And so that transition from the first way of thinking you described to the second is the transition from Newton to Einstein. And
so why is it that we have to go through that in school and sometimes never quite get to the Einstein part?
Well, the short answer is that general relativity is a set of 10 second-order partial differential equations, and solving that is a bitch. So, it's not something you want to present to any poor undergraduate. I had a class in GR as a grad student, and it was a sweat-inducing experience anyway, even then. So Newtonian gravity is a little more intuitive. It's simpler to work with. I mean, Newton's universal gravity equation is fairly simple, and you can work it. And of course, the problem is it has these problems of what the hell is this force and how does it act over a distance? And, famously Newton was asked this, what is this amazing force that acts instantaneously through the vacuum of space to hold things towards each other or pull them in their orbits? And Newton said, I frame no hypothesis. He just sort of blew off the question.
Yeah.
And so the reframing of gravity and general relativity is, in essence, why Einstein is as famous and fated as he is, because it was an incredibly audacious way to take a mature theory that had passed almost every one of its tests, coming from, at the time, through history, the greatest scientist we ever thought lived, into a new form. And I think the way you described it well, of the indentations and the bending of trajectories caused by space-time being warped, the most succinct sort of aphorism for that was by John Wheeler, which is appropriate because he coined the term black hole in the 60s. Mm-hmm. And he said, mass tells space how to curve, and space tells mass how to move. Mm-hmm. And the symmetry there is sort of the explanation of gravity. The particles in the universe, or the planets or the galaxies, they're just sort of unwitting victims of curved space-time, just following it like a crazy funfair ride. And that curvature is caused by the mass and energy in the space itself.
Yeah. I sometimes struggle with sort of the pedagogy versus the, maybe popular science conversations that we often have, where as much as it's really important, I mean, I was just saying this, that it's so important to tell this chronological, historical account of science. I also think it's important at the before and after points to survey, like what we know now. And my concern is that so many young people learn about classical kind of Newtonian physics and then their education stops, that they actually don't have a good understanding of what modern science or how modern science views these kinds of problems.
Yeah, no, that I agree. And that is a real problem. And it's a problem if you're a science student, if you're a physicist, they sort of withhold from you all the fun stuff until you're a senior or a junior. And it's
until you've learned about like Plancks and pulleys.
Yeah, and that's right. And you've done these little electromagnetism or static electricity calculations until your eyes are rolling back in their head. And I went through that too. It just felt like, oh, this is the ritual hazing that I have to do for a couple of years till I can get the cool stuff. And maybe it doesn't have to be that way. I'm not. And maybe if I were into physics pedagogy, I'd be radical and see if things could change.
Okay, so I've already kept you so long, and we're really getting close to the end of the podcast where I have kind of a ritual and I ask everybody the same 2 questions. But before we get there, I want to ask you a question that in my mind feels like it's out of left field, but also because we're talking about cosmology and maybe everything is related in cosmology. I mean, it all has to do with, right, the quote unquote birth and then the growth or the change, maybe we could say, of the universe. My question is, we hear these terms thrown around a lot, like dark matter, dark energy. Dark energy is 75% of the universe. Dark matter is 25%, whatever the case may be. Are those things directly related to our understanding of black hole cosmology, or are they offshoots? Like, is there dark matter inside of a black hole? Like, how do these things play well with each other?
Okay, so it is a good question. It's actually a big question. I mean, we can take a couple of minutes to answer this. So in a cosmic ingredient situation or context, black holes are not that interesting. Let's just say they're esoteric baubles of the universe, because if you do the inventory of the universe, and you alluded to it, it's about 3/4 dark energy, 21% dark matter, 4% normal matter. All the 10 to the power 80 atoms in the universe are just 4% of the universe. The rest of it is these 2 dark things. You could say, well, what about the sum of all the black holes? All the black holes in the center of those galaxies and all the black holes within the galaxies that are dead stars. It's actually 1/100% of the universe. So, black holes they're not a hill of beans in the context of the universe itself.
But neither is the 4% of stuff that we actually know about.
Right. And astronomers have not understood or truly identified 95% of the universe. And, the analogy I use there is, if you had a huge family, 20 kids, and you could only account for one of your kids, you'd be a pretty shitty parent. We're kind of shitty astronomers because we can only really explain and account for 5% of the universe.
So is that what the term dark really means? It means we don't know what it is or how to measure it, and it doesn't put off radiation. So there you go.
Yes, with a little distinction between the two. So dark matter, it's a description of something that has gravity but doesn't interact with or emit light. But in the case of dark matter, at least we played the process of elimination game quite well over 4 decades. So we've ruled out a lot of stuff. For instance, we've ruled out black holes. We've ruled out black holes of any size. We've ruled out free-floating planets. We've ruled out substellar objects, stars that are just too dim to shine. We've ruled out rocks in space. We've ruled out tiny dust particles. So if you put all that together, we've ruled out everything from big black holes down to microscopic dust particles. And so almost by elimination, all that's left is a new type of fundamental particle. And that's where people are looking. So that's some kind of progress.
And that's like what we're doing at the Large Hadron Collider, for example, is trying to figure out what else exists out there that's quote unquote exotic that we don't have technically here.
Right. And then there, and also in a lot of deep mine experiments, I like to use telescopes on mountaintops with beautiful skies and valleys and nice scenery. Those physicists that go down mines and look for tiny subatomic particles, that's not for me. But that's where that's the experiment that might succeed. Dark energy is a different beast. Our level of ignorance is so huge. So literally, dark energy is just a phrase that encapsulates ignorance. We just know that we know that the universe is expanding at an accelerating rate. That observation, at least, has been confirmed and, again, generated Nobel Prizes, so presumably it's right. But the agent that's causing that accelerating expansion, which we call dark energy, we know essentially nothing about it. So our ignorance level is so high. And, of course, into the ignorance marches a lot of clever theorists. And so there's probably 200-300 papers a year written on dark energy, even though we don't know what it is, and astronomers are really almost at a loss of how to design really clever experiments to say what it is. Mm-hmm. So that's where we are with that. Now, the other answer to your question, though, about any possible connection between black holes and the universe itself, is that they're both consequences, they're both concomitants of general relativity. So the expanding universe and its shape and size are straight out of general relativity, and a black hole and its description as an event horizon and a singularity and how space and time are warped near it is also out of general relativity. So it's this exquisite exposition of one theory on these vastly different scales. One, the whole enchilada, and the other, these little exotic baubles of concentrated matter. So that's kind of cool.
Yeah. And so researchers like yourself who are interested in maybe black holes, researchers like my friend Katie Mack, for example, who's interested in dark matter, you guys have a lot of crossover also. Like, you're well aware of each other's work and of what's going on in those fields because they inform you.
Yes, I mean every astronomer is working with gravity and personally subject to it, of course, as well. So those days when it's hard to get out of bed, but we talk, and so luckily astronomy is a small community. 10 times fewer astronomers than physicists, 20 times less than chemists or biologists. So, wow. It's a little easier at astronomy meetings to talk to someone who works on the little black holes and you work on the big ones and say, hey, how's that going? What experiment are you doing now? Or what observations are you doing? And the theory community is even smaller. The number of I once asked someone I team taught with, I used to team teach cosmology with a theorist, a gravitational theorist, a relativist. He was, just as a pure aside, he was a Jesuit priest, and that was interesting in its own right.
Very interesting.
And I asked him, I remember once we were having coffee just planning our lecture, and I said, Bill, you're a relativist, you do general relativity theory, not experiment or simulation for a living. How many people really understand general relativity? And I just sort of pointed to my gut, at the gut level. Mm-hmm. And he took it as a serious question, and he thought about it, and he said, 50.
Yeah.
And that's not very many.
No. And the cool thing is, as you mentioned before, that sometimes, these fields are highly competitive. There's a push to publish. We saw it with BICEP 2. Mm-hmm. We see it across the board. But at the same time, it's this cool thing where, two kind of what we think of as opposing forces, as it will, are happening at the same time. There's an ambivalence here because there's just as much competitiveness as there is real, true collaboration. And you have researchers from across the globe co-authoring papers coming at it from different angles. Yeah,
I would say of my tribe, I talk to scientists. Now I'm a dean. I talk to chemists and biologists and all the time. My tribe they're pretty collaborative. I think astronomers are just generally collaborative, maybe because the tribe is smaller, so you do tend to, after a career, you pretty much know everyone. You run into people.
Yeah. And you have to share tools, right? Because astronomy tools are so big and expensive now that you cannot dominate one.
Right. And I think the other important reason why the astronomy tribe is different and why their view of discovery and that trade-off between competition and collaboration is different is because it's not a zero-sum game. I mean, almost every interesting thing about the universe hit us upside the head and we didn't expect it. There were true discoveries, things that were not anticipated, not predicted by theory. So it's such an open box and such a wild and wonderful place to explore. It's like there's enough for everyone, right? So why would we be competing?
Well, gosh, I have to thank you for helping us explore this wild and wonderful place today. Before we say we bid adieu, I would love to ask you the same two questions that I close every episode of Talk Nerdy with, which are really big picture questions. And of course, you are a big picture researcher. So I want you to think about the future, and you can think about it in whatever context is relevant to you right now. There's a lot going on in the world, but there's also a lot going on out there in the cosmos. And I want you to let us know, number one, what is the thing that really does, genuinely keep you up late at night? Like, what are you truly concerned about, maybe pessimistic about, maybe even a little cynical about, that, you don't have the best feeling about? But on the flip side of that, so we don't end on a super down note, what is the thing that you are genuinely, in a non-lip service way, truly optimistic about, looking forward to when it comes to the future?
So the thing I'm nervous about, and you might hear this from other of your guests and physicists too, is that it feels like as we refine cosmological parameters and measure things more accurately and have these incredible observational tools, there are some deep flies in the ointment. I'm not sure what the right metaphor is. There's when you have the dark energy and dark matter issue framing your entire subject, there's a chance you're fundamentally wrong about one of your favorite theories. So I would say, it's interesting to do a poll like this at a big meeting with theorists and observers. What odds would you place on the fact that we're completely wrong about something fundamental, our gravity theory or the nature of the universe or inflation in the early, whatever your favorite thing is. And most people don't put a small number on that if they're being honest. And so there's some people more nervous about this and more pessimistic than others, but I'm a little nervous because there are some issues of the universe that seem to look like fine-tuning or anthropic, and I don't really like that philosophically, or it's not aesthetically pleasing to me. It's not how I imagine a universe that I would be comfortable with. So so that's what I worry about, that we're really deeply wrong about going hard down some wrong path on something fundamental. And then on the positive side, the tools are so powerful now, with gravity lensing, gravitational waves being the prime example, with, the kind of telescopes we're building. There was a book written by John Horgan, New York Times journalist, a few decades ago called The End of Science.
Oh, yeah. I read that book in a philosophy of science course. I
mean, it was a lightning rod of criticism. For scientists hated it because it, said, well, why are you bothering? And he made some, of course, very interesting arguments. He knew his history. He knew his subject. But in the end, I would refute strongly that thesis that we're converging on the end of science because we've essentially figured it out. There are variations of this theory, like the genius. Where are the geniuses? Where are the Newtons and the Einsteins now? We've run out of those as well. So my optimism just stems from the fact that in any field I look at, and of course I would extend that beyond astronomy through physics, biology, chemistry, the level of innovation and discovery is phenomenal. And of course, now it marries with technology where, you're starting to alter the genome and make new forms of biology. In astronomy, we'll start to discover life in the universe. We'll eventually have nanobots traveling to nearby stars, and the humans will extend beyond the planet. So it's just like science is such a young thing. It just feels like we're just getting started.
Oh, absolutely. Gosh, I really would echo that sentiment in a deep way. And I completely agree about the John Horgan book. Anyway, Chris, thank you so much for joining me. This has been really, really illuminating. Guys, the book is Einstein's Monsters, The Life and Times of Black Holes. And when did it come out? Because I just got the hardcover recently.
The pub date is today.
Oh, no way. Okay, so we're recording this on November 13th, Tuesday, but it's going live just this coming Monday. So guys, it's out now. Make sure that you pick up your copy. You can get it obviously online or in any of your local booksellers, anywhere books are sold. Chris, thank you so much. This was a blast.
Thank you, Cara. I had a lot of fun.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.